Hey guys, thanks for watching. It's Christmas, so first of all, have a nice day, enjoy your family, happy holidays to all of you. I hope you have a great time. On myself, I'm a little bit, I have a little cold, so I'm home alone. Well, everybody's out with the family. But that gives me the time to show you how you can create your own little steam gauge. Now, I already did a little steam gauge. The result worked, but it wasn't, you know, I wouldn't put it on my resume if I'd ever needed a resume to show that I made steam gauges, but that's beside the point. It wasn't beautiful. This one, it just feels like a solid unit. I still need to put a little cap on top and in the back, but I left it off because, you know, I want to show you guys how you can make it yourself. So we're going to be covering that today. I'm going to show you a little sneaky preview at the end of the video about the input handling, like the radio comm signals frequencies. It's so much smoother, but that's coming up this weekend. Trust me, you want to stick around for that. If you like it, leave a like and if you get a bit of subscribe, and let's just dive in how you can create one of these bad boys yourself. Well, as we're able to tell, we have several different pots in our builds. We have the inner ring, goes right here in the middle. We have the outer ring, which fits in perfectly snug in the outer ring. We have room for our plexiglass. We have room for the cables to come from the LEDs to the inside. And we have the holders for our little servo. On the inside, we have our little thingy. I'm gonna push this back because we don't need this. It really wasn't a success. So we're gonna say to object, here we go, cut, yes. So that's gone. We have a flat base. It's, like I said, it's 2 layers. So here I've mounted my little, how do you call it, gear? And here is the bigger gear with the servo attached and the 2 base objects. Let's see if I can enable them. Here we go, yeah. Okay, no, don't put a lid on. Here we have our foot, and this is the other foot, and that's because the gear is a bit of an pointing out, sticking out, so we needed to have a little Z form instead of the straight one. And it has a little indent at the top to make sure that it can slide in because it has this little triangle on the plastic itself. So these parts, they take quite some time to print actually. Not that much plastic though. I believe this was 150 grams for the big block, or 120, I believe, somewhere in between there. But the results are amazing. I mean, let's go back. I made it a bit darker than usual because, you know, just so this would have more of a dramatic effect. So if we've printed everything, it would look something like this. We have our front plates, we have a button. I've already installed it, but we still need to route it. So I'm going to show you later on how you can do that. And we have our gear in place. For this we need an Arduino. I've used a Nano, but you can use any you'd like. I'd even recommend the Pro Micro, I believe. But the Nano is fine, goes with the micro USB. And last but not least, we need our servo. I already glued my gear on. The most important thing to note here is that on the servo, there is a bigger gear that drives a smaller gear that's attached to the needle. Now, a servo has 3 wires. It has a ground, the brown one. It has the power, the red one. And it has one that can control the servo, the yellow one. So let's put it aside for a second. Now, our Arduino is gonna be mounted somewhere at the bottom. And our servo is going to be somewhere in those white brackets. We have our 3 LEDs that are already hooked up with a 220R resistor because I wanted quite bright lights because it really was meant to lighten up the gauge and not to act like some sort of status light that doesn't need to emit that much light. So I went with 220R, which is at the low end, perhaps even for white, but they get some nice brightness and they can just fit in at the top. Now, our 3 LEDs are already hooked up to each other via the ground wire. So the ground goes from one LED to the ground of the other LED to the ground of the last LED. Now, the only thing we need is another wire to ground that goes to the button. So all our devices are going to be on the same ground line. So from LED to LED to LED to the button to the servo to the power that comes in through our adapter, and then through our power of our ground of the Arduino board itself. And now we can just mount it on top right here. We're going to be adding some cables later on, so I'm not going to glue it in already, just so you have get a gist of how it will all fit later on. Now, for those of you that perhaps are completely new to this channel, LEDs have a positive and a negative side. The long side, so the longest foot or leg, is where the power comes in, and the shorter one is where it comes out. You're able to bend these pins at no issue. You can even cut them off, like I did in the example below. It's just to make sure that you connect the ground to the ground, so the short to the short and the longer to the longer one. Now let's push the ground cable in so we can start wiring it up to our button. Me myself, as you might be able to tell, I took quite a long wire, and that's because I like to have it long and then cut it off once I know that it can reach the button, instead of being really precise and then cutting it wrongly and having to do it all over again because the cable is too short. So now the LEDs are all connected together and to the button as well. Because it's quite a short cable, I'm just going to leave it all up here and we come back to it later when we need to. Now, to power the servo, I'm going to be using a buck converter and a wall adapter. It's because I have a 12 volts adapter, while the servo only uses 5 volts. And I couldn't be bothered to go buy a 5 volt adapter. So if you have a 5 volts laying around, you can emit the buck converter completely. In my case, I needed to convert the 12 volts to 5 volts. It will fit something like this, and we need to find a place for the Arduino as well. And this is just to make sure, because the servo requires quite some power, even so much that it can like reset the Arduino itself because it just draws too much current. The next step was to just cut off the connector of the servo it came with, because it had this little connector thingy on it. So I just had the wires, I stripped them, and I wired them directly to the ground and output of the buck converter. I'm going to be using the buck converter to power the servo, so we can just hardwire it on. And later on, we have to make sure that we also wire the ground of the buck converter to our Arduino board. And now the end result will look something like this. We have our servo with the ground going to the buck converter or the power in, depends on your situation, and the ground going to the ground. And the control line is still open and hanging loose. I'm going to wire up another ground line that goes from the last LED into the case, and this is the ground wire that goes from the LEDs towards the buck converter. So in our case, we've hooked up the button to all the LEDs, so we could either choose to go from the button to ground somewhere on the board or somewhere on the buck converter. But in our case, I've chosen to just go from the left side because I had more clearance over there to draw a wire all the way down to where the buck converter is going to be. Well, now last but not least, we've hooked this up to the buck converter. Now we need to hook up the last ground wire at least that goes from the buck converter to the board. So now we've got everything hooked up together on the same ground line. So we have the board, we have the buck converter, we have the servo that's directly attached to the same point, and we have all the LEDs and the button. Now we're still missing some cables, and that's from going from the LEDs to our board to actually control the LEDs, and of course the wire that goes from the button to our board and the servo. We're able to tuck all the wires of the LEDs through the top hole, and we can just leave them hanging for now because later on we will route them to the right. Now I was pretty stupid to already mount the button in, so now I have to go in here and solder it from inside of the box. So if you have any possibility to do it outside of the box, please do so, because this can be quite hard and you have to. And now last but not least, we make sure that everything's connected to our Arduino. I've connected everything to a digital pin. That's all fine. It doesn't have to be a specific one. I believe I've gone with 12 10 and 8 for the LEDs. I've went with 13 for the servo and 5 for the switch. So it's a bit up to you. You're free to do whatever you'd like. It's just where I happen to place them coincidentally. And just for testing purposes, I'm just going to fit everything in here from the servo to the Arduino, so we get a clear view of what is all going to be in there. We're first going to test things before we actually glue it all together. Now, for keeping everything in place, I went with the easy route of adding glue for my hot glue gun, so that will keep my LEDs in place and even my servo, buck converter and Arduino just fine. Just a little thing that I did is even keep cable managed a little bit to make sure that the servo cable didn't fall into the gear, is by adding some hot glue as well, making sure that it doesn't fall down. Now, I do have to note, be careful, because it's really hot glue. Now, perhaps I'm not even talking about hurting yourself. I don't know. Perhaps it will hurt a little bit. I don't know. I haven't gotten that on me yet, but be careful with the plastic, because it can actually leave some burn marks on it. So don't do it on too fragile surfaces. Now, in my example, I already put the plexiglass in, and I'm gonna move the hole of the button to the lower part, so you can just flip the entire model. And that's because in my design, you can't remove the plexiglass without having to unsolder the button, because it's in the way. But enough tinkering, let's just go straight to the coding, shall we? So let's just dive in and see how you can program your own steam gauge, because this one is so much better than the one I had before. Like, let's see if I can get it on camera. This one, it's, I don't know, look, at the printer gave up ink halfway through, so you have those lines in it. So that isn't all too great. Okay, so we're going to start by including the library, right? Because we want to get the data from the game and send it over to the Arduino. So we say hashtag include bits and droids flight connector.h. You can download this from my website. I'm going to put the link in the description as well, so don't be afraid that you don't have it. You just have to download the zip file, and in the Arduino IDE, go to Sketch, include library, add.zip library. And that will do all it needs for you to do. So you don't have to do anything anymore, just include it in the project. And because we're working with a servo, we're going to do include servo.h, which can be found by going by tools, sketch, include library, manage libraries, and then just search for servo. I think it's already on there by default. I'm not quite sure, so I'm just showing you where you can find it. Servo. In my case, it's already installed. I can update it, but I'm not going to do that right now. Probably at the end of this video I will, but you know, I just need to get the train rolling. So we're going to say bits and droids flight connector, because we need to create a new connector object. And we're going to say false, because in my case, I'm using an Arduino Nano. If you're using Leonardo or Pro Micro, you need to put this at true. I think I got this. Oh, I think I got a shortcut set up somewhere. Let me quickly. Here we go. No, remove those. Now it should be fine. Yeah, so we need a connector object. We also need a servo object, so just going to do my servo. We need a servo position. I'm going to explain everything in a second about why we need him. We need the servo where it's connected, so the pin, in my case it's at pin 30. We need the speed value that's actually coming from the game. So in our case, let's by default put it at 0, just to have a baseline, right? And we need the int LED1, int LED2, and int LED3, and int switch. Now mine are hooked up to LED1 is hooked up to 12, LED2 is hooked up to 10, and LED3 is hooked up to, where is it hooked up to? It's hooked up to 8, and the switch switch. Now let's call it btn, of short for button, because switch is apparently a function kind of. So the button is at 5 in my case. If you wire up differently, please change these pin values to your own pins. I'm just gonna put this one here as well to give a more clear view. Here we have some values and here we have the pin defined, right? And we need a little boolean to say if a light is on or off, because we want that fancy light to, work if you press the button. So we're gonna say bool light state is true, false, because by default we want it off. Okay. So in this setup, we do my servo dot attach, and we give it a servo pin. So up here we said our servo is connected to 13, and here we say in this library we want to attach the object of the servo to the actual physical pin at 13. And now we need some LEDs, right? So we say pin mode. LED 1 is an output, because we want the light to go out. It doesn't give us a signal coming back. I'm just going to copy this and paste this 3 times and change the 1 with a 2 and a 3. There we go. And we say pin mode btn, so the button is going to be an input underscore pull up. So now we have a button and we have 3 LEDs, and that's actually all there is connected, so we don't need anything more. I'm using a nano, so I need to do serial.begin 115200. And we need to make sure that the Arduino doesn't take a full second to handle the incoming serial lines. We do set timeout 15. Now let's remove this comment. And let's start working on our code, right? Well, the easiest thing to start with is just the light. Because I want it to be that you just press the button and the light goes on or off. You could also retrieve the, let's see if I have it in here. Warnings, lights. You could create a function that said if the cabin lights are on or panel lights, I want that light to be on as well. Or wire it up in a case that if you press the button, the panel lights go on, which I'm going to come back to tomorrow or the day after tomorrow, because I found a way to directly input our commands to the game, so we don't have to use a joystick library. And especially if you use rotary encoders and you've been using the joystick library and you've been turning it in game, it could be quite frustrating at times when it would skip a beat. It wouldn't be fluent. It would sometimes stagger, go up, go down when it's supposed to go the other way around. If we do it directly, it's all gone. The main issue that still exists is that sometimes, like 1 in 20, 30, 40, 50 clicks even, you don't even notice it. It goes up by 1 or down by 1. So the error margin is reduced significantly, and it becomes fun to actually change the radio channels again instead of a chore. So that's coming up this weekend. If you want to stay updated, subscribe, and let's just continue with this code, right? So we're going to take the easy route. The button just turns the light on of the screen itself. So let's say, why do we, if button, a digital read, because we want to read the status of the button. So we do digital read, and in the brackets we do btn is equal to low. So if the button is pressed, we want to do something. We want to change the light state that's currently by default at off to on. But if it's on already, we want to turn it off, right? So we say if digital read button is low, we're going to do, in the if statement, we create another if statement, if light state. So it's just going to, because it's a boolean. So if you say if light state, it's already going to return us the value. So in this case, false. So if it's false, this one got executed. But if it's true, it would. So we say if it's true, we do light state is false. Now what do we do else? So if it's false, we say light state is true. Okay, here we go. Now create a little function void toggle lights. And we could even create, oh, you know what? We're not even going to use the Boolean, I think, but no. Void toggle lights, we're going to use the Boolean, but whatever. So if light state serial dot, not serial dot write, digital write. What do we want to write to? We want to write to LED1 and we want to say hi. So if the light state is on, oh, I did the braces wrong, sorry. So if it's light state true, so if it's on, I want to do let1 high, but I also want let2 and let3 to be high, right? So I'm going to say let2, let3, and else digital write LED1, once again, close it, and we say low. So this function, all it does is if it gets called, it's going to check if the light state is true or false. We could also do this part up here. Let's do it up here. So if light state, it's going to check if the light state is true, it's going to make it false. And the other way around. And then it's going to say, okay, if the light state is true, turn it on. If it's false, turn it off. So the only thing we need now in our button click is a call to our function. So we say toggle lights. Oh, we don't have to pass any parameters. And this should already suffice. Now let's just do a quick test because, you know, why wait to test it when we've added more codes and then something doesn't work, etc. I typo, I think. I forgot to close the line. Upload. And I made another mistake. Digital write. LED3. Digital writes. Oh, okay. I see what I did. I put all the brackets wrong. Whoops. Now it should work, right? If I'm correct. Okay, that's working fine, right? The only thing we need is a little delay, because you see it sometimes triggers twice when I'm only pushing it once. And that's because we don't have a delay to actually freeze the toggle. So it keeps, if you push it once, maybe it registers twice, goes on and off. So we just do a little. You know, it's a bit like Bob Ross, you know, you create a tree, you use a little delay and all is fine. Get some quiet and calm to our toggle, or our toggle of light. I'm gonna have a look, throttle, and here we go. I'm gonna press the button, and the lights goes off, and the lights go on. So as Bob Ross would say, it's just splendid. See, that is working fine now, and it doesn't trigger twice. So we got the lights working already. That's faster than I would expect. Now, if you take a look, there is a divide, right? We have 40, 60, 80, 100, and this is pretty spread out. And then we have 120, 140, 160, 180, 200, which are closer together, especially 160 to 200 are really close, and the 100 to 160 still have some space in between. So we're going to tackle that it isn't a clear division, so we need to do something with it. Well, the first thing we can spot is that the 40 till 100 is a section, 100 till 160, and 160 to 200, right? So let's just write that actually just as a comment to give us a bit of a reminder. We have 0 to 40. We have 40 till 100, I said, and we've got 100 till 160. Oh. And we've got 160 till 200. Now, I already did a little bit of testing. So what we're gonna do is just write something to my servo. So do my servo.write. And let's say we first want to get a baseline for the 40, right? That's the first number we encounter, and where our needle is gonna point. Our servo can write from 0 to 180 degrees. And because we use gears, you know the range is extended. But the values are going to be between 0 and 180. So if in this case I would pass the value 15, let's just upload it and see what happens. Here we can see that it actually turned to 40, right? So we know that the 40, so 40 is equal to 15 on our servo. Now if you would want, let's say, so this is 0 till 15, right? What if we want the upper region of this one? We already know that it's 15. And where is 100? Well, let's say, in my case, I closed it off. 0 till 40 is our bottom range, and we already know that it's from 0 till servo position 15. Now, if we want 40 till 100, we know it's from position 15 up until, well, in my case, I know it's 80 because I already tested it. So I'm going to show you if I change this to 80. It goes to 100. So this is something that requires a bit of trial and error, right? Because I started with some, let's say I started at 70. I see it needs to go a little bit further. And I just write for myself, write down that 100 is located at 80. Now we do the same with this one. We know that this starts at 80 and 160. I didn't check this one actually. So let's say 120. I forgot that I made a division between 0 to 40, 40 to 100, and 100 till 200. But in this case, that's not correct fully. So let's see, 120. Oh. It's going to give us, no, we need a little bit more. 130. And see, that's the kind of thing I'm talking about when I say it's a bit of trial and error. I hate that word. It's just testing. 150, because I need a little bit more of a jump, because we say up until 160, right? That's actually pretty accurate, 150. So we're going to say 150. So we go back to our codes. We say 80 till 150. And now we already know that the upper region is between 150 and 180. So we know that servo position 0 till 15 will cover our speed positions of 0 to 40. 40 to 100 can be found at 15 to 80. 100 till 160 knots can be found at 80 to 150 on the servo. And 160 up until 200 can be found at 150 to 180 on the servo. So this will just give us a nice baseline. We kind of calibrated where our servo would position the needle based on the values we feed them, right? Because we know that a plane will go perhaps a bit higher than 200 if it goes down really fast. But we're just going to cap it out at 200 because we don't have any more meter available and we don't have the servo that goes 360 degrees. So this is something that we're going to have to work with. So in this case, we're going to use these values as also brackets to divide the motion. So how are we gonna decide how to divide them? So we say speed val. We already said we had an integer up here that is going to contain the speeds we're currently at. So the speed val is the connector.get indicated airspeed, and we need to do it to convert it to an int because it comes back as a string. So this is going to give us the value from the game. So let's say 40, right? If we go 40 knots in game, this value will be 40 as well. So we know in the first bracket, if speed val is smaller than 40. And it's going to contain this entire bracket, right? So we're going to do, here we go, paste it in down here. So it's going to be clear that this code contains the range 0 to 40 knots and 0 to 15 on the servo. So we're going to do int, going to create a new int actually. You're going to say int position, so position servo. So we actually know what we're talking about. You know, sometimes it's best to have a bit of a longer name in your variable as long as you look back at your code and still know what happened, right? That's more important than have short, unreadable code because you can't remember what. You could also do this, call it X, but nobody's going to know what X was, right? Especially if you look back at it a year from now. Or perhaps you do, but I wouldn't remember what X means. If I see position servo, I know exactly what it's about. So if it's lower than 40, we're going to say position servo. We're going to use something new. It's a map, and we're going to give it the speed value. We're going to give it the lower value of our knots, so 40, of our knots range. So we say then the upper max value is 40 in this case, in this bracket. We give it the lower value of the servo, so 0, and we give it the upper limit of the servo motion as well. So if it's below 40, we know that the position is going to be set off, because this node is a value between these two, and where on the scale does it lay for this one. So if we would replace this all with 0 to 100 and 0 to 100, if we would enter 60 here, it would return 60%, because 0 till 100 is 60%, and 60% of 0 till 100 is 60 as well. So in our case, it's going to check for the speed val. At which percentage can it be found if it goes from 0 to 40? And at which percentage do we need to put the servo then? Right, so it's going to return an integer, and it's going to store it up here. Now, if speed val is bigger or equal to 40, because here we said it's smaller than 40, so 40 wasn't covered yet, right? It would cut off at that point. And let's just say speed val is smaller or equal to, no, let's do smaller, 160. Here we go. So what did we do before? We do exactly the same. We do position servo is map speed val, but now we're not going to check on the scale from 0 to 40 because we know it's going to be between 40 and 160. So we say 40, 160, and then it's going to be at 80 and 150. Let's just to create a more cohesive story, right? I see I already made a mistake, right? Isn't that correct? Yes. 40 till 100, so not till 160, 100. So now we change this to 100 as well, and it's 15 till 80. I took the wrong lines. So it's always good to double check what you're doing. Do exactly the same. If speed val is bigger or equal to 100, and so we do double ampersand. Is it ampersand? I don't know. Speed val is lower than 160. Right, so we do exactly the same, but we change the values once again. So here we go, just copy paste speed val, but this time we go from 100 till 160, and we're going to give it the values of 80 till 150. And the only thing that's left, else position servo is map speed val 100 to 200. We're going to give it a range of 150 till 180. Whew. So we made a division where it would return us a percentage based on the incoming value. It would split up into the correct brackets, and then give us a percentage of the servo position. Are we still following along? So if now we would say my servo dot right position servo. Let's see, let's put these in there as well in the code so we know what we're talking about. Oh no, this one 160 till 200. Here we go. There's still a chance that it's going to be bigger than 200, so we're going to intercept that situation. We're going to say if speed file is bigger than 200, position servo is 180. So it's just going to be at max. It isn't going to, I don't know what would happen if we try to force it over the limit, but you know, just it's better to sometimes be thorough than not, right? So we could test this by doing a simple thing, saying speed val is 80. If I did everything correct, it should go to 80 on the meter directly. I made some typos, I think. Position servo. It's not declared in the scope. Position. Oh, did I make it a postion? No, that's not a position. Position. And that's what you get when you copy and paste everything, because now it's going to be in here. Position. Okay, yeah, now it should be fine. Perfect. So let's go to our right camera. Get the camera, mom. Oh boy. Okay. Something's going wrong, right? I'm saying speed fell. Oh, I'm sorry, rough. I already also included still the first debug where it says 150. Okay. So what I did wrong is I made an else statement of the last statement that said else, but it should be if speed val is bigger or equal to 160. And why is that? Why is that the case? It's always going to be else, because it's going to just go run through this code and it's going to hit the else block, and you know, it's also going to be that one. So in this case, we just needed to make another if statement if speed val is bigger than 160. So get rid of the else and replace it by bigger than or equal to 160. And now if I would do 120, it would go hopefully to 120. Right, yeah, a little bit off, but that's because, let's see, 100 to 160, 80 to 150. Could be right, I don't know. Let's say 140. Just gonna do some little random tests. Could be that I'm a little bit off on some of these values. 140 is good enough for me, 160. And it could also be that I just placed them a little bit wrong on the design itself. So I'm going to be satisfied. 160 is off by a lot though. So it's bigger or equal to 160. We said going to be between 150 and 180. If it's smaller than 160, smaller or equal, and we're going to say bigger than 160. Let's see how this works out. Yeah, now it's fine. So if you want to really nail it down, you could spend more time on that part of the code. The only thing that's left is to, you know, get the data from the game. So how do we do that? We uncomment this line. Speed val is connected to get indicated airspeed.toInt. Just remove this, upload your code, and it's going to pass us 0. So it's going to start a little bit before the 40 if I'm correct. Yeah, perfect. So we have our game open. And I'm gonna depart, you know, it's Christmas. Guys, it's Christmas time. I'm gonna depart from my home airport, Amsterdam, Schiphol, just so I could be home for Christmas in time. If you wonder why I'm all alone at home with Christmas, it's because I have a little bit of a cold and I didn't want to murder my in-laws, at least risk to make them ill or something. So I stayed home, especially in this time, you know. It's a bit of a thing if you come in sneezing. So I decided to stay home. My girlfriend's over there. But that's fine, you know, that's the time we live in, to say. And while it's loading, we're gonna start our input connector handler. I'm gonna turn off the lights because, you know, we put lights in there. We're gonna want to use them, so I'm gonna be in the dark. What do we want? We want the indicated airspeed, right? Yeah, that's right. I'm just gonna start it. I know mine is connected to COM6. Okay, so something technical went wrong, so I have to do a little retake, but doesn't matter. We're gonna fly COM6. Already started the input as well. I'm gonna restart them actually. And that's because I'm gonna show you how the radio works right now, because it's so much smoother.
Sierra, X-ray Golf, Sierra Alpha ready for departing straight out at runway 27.
Okay, so here we are right now. Let's first, I'm gonna show you the... Let's shove this up a little bit and get this in shot. See this rotary encoder? And see this radio frequency? Look how smooth this is. It doesn't skip. I click and it changes from kilohertz to megahertz, and it's just so much smoother. It doesn't jitter all over the place, and it's just amazing. And I've got a whole set of these commands lined up for you guys to use in one of the coming updates. So that's coming up this weekend. Stay tuned. Now let's get back to our little steam gauge, shall we? A bit more vision. I really like the new update where they made it possible for the Xbox controller to use the rudders as a axis instead of a hard left, hard right. And as we expected, speed meter is going up and we're off. There we go, flaps in at 300 feet if I'm correct, right? And it's actually quite accurate, so it's 80 right now and it's 80 at the meter as well. And it looks so fancy, it's just the reflection is a bit... see, it makes it looks worse than it is, because it's actually pretty smooth and worked out. Even with the lights on, it looks pretty well in real life, but my camera doesn't capture the beauty of it all that well. So that's it. That's just how you can use your steam gauge and make it look actually sexy instead of what we used to have before. Wait, let's first, you know... Ooh. Look at it go. That's... Ah! It's perfect. I just wanted to do this just to get the real fast movement on the needle. Beautiful. Perfect. Perfect. Okay, so thanks for watching. As always, if you have a question, leave them down in the comments below. I will put all the links to the downloads like the exe to get the data from the game, and where you can get all the components I've used yourself. So you can find it all in the description. I will also sticky post one of those comments down below, so you can always find what you need. As always, thanks for watching, and I hope to see you in the next one.